We have been looking at inductances in machines. We have been considering electrical machine with a cylindrical stator and a salient pole rotor with one coil each on them. We have derived expressions for the mutual inductance between the coil on the rotor and the coil on the stator. We have derived an expression for the self inductance of the rotor coil, and we were beginning to look at an expression for the self inductance of the stator coil, which we shall try to do in this lecture. The difficulties we encounter for this are: one is that the flux density waveform, flux density distribution around the air gap would not have a constant wave shape. And because of this, it also further, in addition to this, it we could say that the flux levels in the machine also change with respect to rotor angle. That means, if the rotor is going to rotate, then depending on where the rotor is, you may have large flux levels in the machine or you may have low flux levels in the machine. For example, let us look at this FEM result. Let us so here we have a finite element study of a simple machine geometry. Yeah, it's better to go to the next page. So here we are. Now here we have the geometry that we were discussing: a cylindrical stator and a salient pole rotor. The rotor is horizontal in this position and has rotated by a certain angle, rotates further and then becomes vertical, rotates further and is again on the way to becoming horizontal again. Now here, if you see, the flux density levels in the rotor are quite high. The flux density levels in this place and this place are quite high. If you look at what that level might be, this table says that the flux density in that area is likely to be greater than 1.5 Tesla in the middle, and then goes down to about 1.27 Tesla or so, and then that is distributed here. In this position of the rotor also, you find that there is considerable flux density here. In these simulations, the stator winding is excited, there is no excitation on the rotor. So here also the flux density levels are high, but as the rotor rotates further, you now find that the flux density levels have come down. Here the flux densities in the middle of the rotor are likely to be in the range of about 1 Tesla, and indeed when the rotor becomes completely vertical like this, then the flux levels are quite low. It is only in the range of about 0.6 Tesla in the middle, and at the pole face, however, it is little higher. Pole face could probably have a flux density level of about 0.9 Tesla. Now as the as the orientation becomes this way, now the flux density levels again increase, and as the rotor aligns itself to the horizontal position, the rotor flux density further increases. So you see that as the rotor moves from a horizontal position, goes towards a vertical position and then rotates again to a horizontal position, the rotor would have moved by 180 mechanical degrees if it becomes horizontal again, and you see that flux density levels itself are undergoing a change. And we know that inductance is nothing but flux linkage divided by how much current you are exciting it with. This is the stator inductance, and if this flux linkage is going to change with respect to rotor angle for a given excitation, this then implies that inductance changes with respect to rotor angle. Indeed, that is what is seen in this figure. The inductances are also marked. In this position we have a stator inductance at the level of 40.5 millihenry, it goes down to 40.31, then 34.09, at this position it is only 30 millihenry, and then it builds up again, right. So we have therefore inductance changing with respect to the rotor angle. How about the flux density distribution? Now let us look at how the flux density distribution around the air gap will look for a salient pole machine. Again we will see the results from a finite element study of a simple geometry. Now this plot shows how the flux density levels are going to vary. The x axis indicates the circumferential distance travelled around the inner circumference of the stator, the y axis denotes the modulus of the normal component of flux density. So let us just call it as B. Now you see this plot has been drawn for rotor angle at 0 degrees. So you see that the flux density is low in this area, becomes high here, goes low here, inverts in sign, becomes high here again. Why is this high here? It is in this region that the pole phase occurs. So if you notice here, the pole phase occurs in this area, this is the pole phase region of the rotor, and you find that there is very high flux density levels in these areas, and as you travel away the flux density becomes lower, and that is what is shown in this plot. Flux density levels here are high and elsewhere it is quite low. But what happens when the rotor moves? This plot is drawn for a rotor angle equal to 30 degrees, and you see here that flux density level here and here are high. The rotor has moved such that the rotor pole faces are moving towards this end, and wherever the pole face is encountered, those regions have high flux density. Wherever the other regions of the rotor are there, the interpolar regions so to say, they have low flux densities here. As the rotor rotates further, this plot is drawn for 60 degrees of the rotor angle. Here you see again it is this region where the pole face occurs is having high flux densities, again the interpolar regions have low flux density that are there. Now here this plot is drawn for 90° of the rotor position, that means rotor is vertical. So here again we see that this region corresponds to the pole phase area, so flux density levels are high. This region here again is the other pole phase, flux densities are high. This is the interpolar region, flux densities are low. Now you see that as the rotor rotates, the flux density distribution around the inner circumference of the stator, the wave shape itself undergoes a change. The wave shape undergoes a dramatic change. Therefore, we will not be able to resolve this into a Fourier series expansion, a fixed Fourier series expansion. The wave shape is going to depend on where the rotor is, and if we are to go and expand this by Fourier series, we will have to do a separate Fourier series expansion for every rotor angle, and it is not going to lead us anywhere, and the wave shape is also not going to be fixed. How this shape is going to look like will depend on the particular machine that you are looking at, depending on how broad the pole is, how much the interpolar air gap is, how the rotor is shaped, how the stator is shaped. All those will have an effect on how this distribution is going to look like. Therefore, it is impractical to try and determine the flux density waveform and hence the flux linkage of this machine. Though you find that this appears to be a difficult issue to handle, all hope is not lost. If we however look at the variation of inductance, now let us look at another plot which shows the variation of inductance. So here you have a plot which shows how the inductance is going to vary for the stator as the rotor is going to rotate. Now the x axis gives the rotor angle and the y axis describes the inductance. Now you see that the inductance waveform is not all that distorted. Even though the flux density waveforms here, wave shapes are going to change as the rotor rotates, the inductance wave shape appears like a rather smooth curve, and in fact it may be feasible to approximate this by a sinusoidal waveform. And indeed, if you look at the next plot where a sinusoid has been superimposed on this waveform, this variation of inductance, you see that this inductance variation could probably be nicely approximated by a sinusoidal wave shape. The red line here shows a sinusoidal approximation to the blue line, which is the inductance waveform. If we look at this, therefore, since this waveform is going to be a sinusoidal waveform, we could probably handle this situation as follows. Instead of looking at the flux density waveform, we start with the MMF waveform generated by the stator, generated by stator windings. For the inductance expression we derived earlier, we looked at the mutual inductance between the rotor and the stator. We derived an expression that consisted of a fundamental component and then a third harmonic and then a fifth harmonic and so on, and we said that it is good enough to approximate this by the fundamental alone. And here we have a sinusoidal variation. It should be enough to get a sinusoidal variation by looking at the fundamental component of the MMF waveform that is generated. So we take the fundamental component of the stator MMF waveform. The stator MMF, for a given angle of the rotor, the stator would generate an MMF that has different values as you travel around the circumference, inner circumference of the stator. And what we are saying therefore is that let us start by assuming that this variation of MMF that happens as you travel around the stator is sinusoidal in nature. That is what we mean by the fundamental component of the stator MMF. So, we are assuming a sinusoidal variation around the air gap. This assumption is not bad, because as you look at the actual MMF in machines do not just have a single coil on the stator. Electrical machines have a distributed stator which is there, and as you go for the distributed stator arrangement, distributed stator winding arrangement, you find that the MMF that is generated by the stator winding becomes more and more closer to a sinusoidal distribution, and it is enough therefore if we consider a sinusoidal variation, that is fine. So, we consider a sinusoidal variation. Now what? Where does the sinusoidal MMF act? As the rotor is going to rotate, we find that the air gap that the MMF is going to face will change. So, let us look at this picture. Now, let us say we look at a given angle on the circumference of the stator. Let us say we are looking at this point here, the same angle as you travel around the circumference. Now, at this point you see that the air gap that this region is going to face is pretty large, whereas when the rotor rotates to this position, the air gap around this region is very small, which is that of the pole face. Again here the air gap is pretty small, but here the pole face is just leaving this region. Here again the air gap would have increased in comparison with this. Here again the air gap is fairly large, and here is a still larger air gap. So, as the rotor is going to rotate at any given angular location on the inner circumference of the stator, as the rotor rotates, because the rotor is a salient pole rotor, the air gap is going to vary, and therefore even if we know what is the MMF at this place and we assume that the MMF variation around the circumference is going to be sinusoidal, we still do not know what is the air gap on which this MMF is going to act. Again, if we look at the flux density distributions which determine which is the result of flux flowing in the air gap, what we see here is that wherever the face of the rotor pole occurs, those regions seem to have fairly high flux densities. Wherever the interpolar region occurs, those regions seem to have low flux densities. This is something that is valid across all these waveforms. Interpolar region, low flux density. Wherever there is the rotor pole face, you have high flux densities, which means, and the interpolar area or the face of the rotor pole where it occurs will depend upon the rotor angle. So, as the rotor rotates, now the interpolar region is here in this area, but if you look at here, this area will now slowly contain the pole face. Here it has the pole face fully, and as the rotor rotates, this area becomes interpolar region again. So, if we look at the way the machine behaves, it appears as if interpolar regions are associated with large air gaps and low flux densities. Whereas pole face regions are associated with small air gaps and high flux densities. And where the interpolar region will occur and where the pole face will occur will depend upon where the rotor is. At any given angle, that may be an interpolar region or it may be a pole face region. So, that depends on the rotor angle. So, even though we know the MMF that is there at a particular angle, because we have assumed a sinusoidal variation of the MMF around the air gap, the actual gap across which this MMF is going to act will depend upon where the rotor is. At some instance at a given angle it may be a pole face, at some instant it may be an interpolar air gap. So, in order to address this issue, the idea that is used is that we assume that there are two air gaps in the machine. Assume that there are two air gaps in the machine and these two air gaps are uniform air gaps. It sort of amounts to saying that you assume that instead of the salient pole rotor that is there, you have, instead of the salient pole rotor structure, you now have two cylindrical rotors one of them giving rise to a small air gap and another giving rise to a large air gap. We further note that the interpolar regions are always associated with low air gap, with large air gap and low flux density. Pole face regions are associated with small air gaps and high flux densities. Therefore, the small air gap equivalent is representative of the pole face regions. The large air gap rotor is representative of the interpolar region. And the region of the pole face is going to be rotating as the rotor rotates. The interpolar region also changes as the rotor rotates, and therefore, in order to find out the MMF that is acting along the small air gap cylindrical rotor or the large air gap cylindrical rotor, how do we find out what is the MMF that is acting? What we try to do is resolve the sinusoidal MMF sinusoidal stator MMF, we have assumed that the stator MMF has a sinusoidal distribution around the inner circumference of the stator. We now resolve this into two parts, one of which lies, or not, maybe a better word would be, one of which is oriented along the pole face, another which is oriented along the interpolar region. And then we say that that component of the MMF which is oriented along the pole face is the one that acts along the cylindrical rotor with small air gap. The stator MMF part that is oriented along the interpolar region acts along the air gap which is larger. The actual flux, now the MMF acting along the small air gap will produce its own flux, and the MMF acting along the interpolar region for the large air gap will produce its own flux. Then the net flux that is there at a given angle is then the sum of these two fluxes, flux acting along the small air gap rotor plus flux acting along large air gap rotor large gap. These two together is then flux at any given angle. The idea is that the flux generated at any given angle, it is not possible to determine just from the MMF distribution alone, because the salient pole rotor is, we see that the pole face regions are the ones that are associated with higher flux density, interpolar regions are the ones associated with low flux density, and as the rotor rotates, where the pole face occurs, where the interpolar region occurs, both are going to change. So we now consider the rotor to be composed of two cylindrical rotors, one having a small air gap, one having a large air gap, and resolve the MMF along these two axes, and then you find out the net flux. This approach has been called as the two reaction theory, and is attributed to Blondel. So it is called as Blondel's two reaction approach. So how do we then do this? Now let us say that we are now drawing, let us take a previous figure that we have used. So this shows now the geometry of the system that we are having, and as you travel around the inner circumference of the stator, you are going to traverse a particular angle. That angle alpha equal to 0 starts here, let us assume that it starts here, and as you travel around, you go from alpha equal to 0 to 180 degrees and then come back as 360 degrees. And if we have the stator coil being excited and we are going to plot the MMF distribution, we have assumed that it is, we are looking at the fundamental component of the MMF distribution. So that variation can be plotted in this manner. So, you have the angle travelled around the circumference and you have the MMF, let us call it F. This is 90 degrees and then 180, 270 and 360 degrees. So, the MMF distribution, since we have considered it to be sinusoidal, will then look like this. It reaches a peak at 90 and then 180 it goes to 0, reaches negative peak at minus 270 and then goes to 360 degrees. This is the fundamental component of the stator MMF. This is the variation of the stator MMF as you travel around the inner circumference. Note that this reaches a peak at an angle equal to 90 degrees, that means at alpha equal to this angle, this is alpha equal to 90 degrees, it reaches a peak. So, this is then the axis of the stator winding, stator coil that is there, this is the axis of the stator coil, that is this line, that is the stator coil axis. And let us further consider that the angle of the rotor when it is horizontal is 0, that means this axis is also coinciding with the rotor angle axis. This refers to theta r equal to 0 and the rotor at present is aligned, the midpoint of the pole face defines, let us say we define the rotor angle. So, this is now your rotor angle theta r. What we have said is that we take this fundamental component of the MMF distribution of the stator and we find out resolve this along the pole face of the rotor and another component which is perpendicular to the pole face of the rotor, and you see that this component then lies always on the interpolar axis, interpolar area. This component, as the rotor is going to rotate, you always resolve this MMF one along the pole face axis. If the rotor were rotated to some other axis, it would still be resolved along that pole face axis, and 90 degrees to that would always lie along the interpolar area. So, this is what we do. How to do that? Now, let us say that the peak of this MMF distribution is f hat, then f hat lies along this axis, f hat lies along the axis of the stator winding, and a component of f hat that lies along this theta r can then be given as f hat cos theta r. And that part lying along this axis, the interpolar axis, will then be f hat sin theta r. We will call this axis which lies along the pole face as the direct axis, lying along the pole face. We will call the axis lying in the interpolar region as the quadrature axis, since it is 90 degrees to the direct axis. Therefore, we call this as Fd, we call this as Fq. Now, Fd has a maximum. Now, the original MMF distribution is a sinusoidal distribution around the air gap, and therefore, the resolved MMF should also be a distribution around the air gap, and the MMF resolved along the direct axis has its maximum value at the direct axis and is subsequently sinusoidally distributed elsewhere, and therefore, we can write this as the total distribution as cos of alpha minus pi by 2 plus theta r. This would then be cos of alpha minus theta r. So, this expression describes the original stator MMF resolved into a component along the direct axis and distributed sinusoidally around the inner circumference of the stator. This expression describes the stator MMF resolved along the interpolar axis and distributed sinusoidally around the inner circumference. If these are two parts, if these two represent the original stator MMF resolved into two components, then it also stands to reason that if you add these two, you get the original distribution back. Do we get that? Let us try to add these two terms. Fd plus Fq is then equal to f hat cos theta r cos of alpha minus pi by 2 minus theta r plus f hat sin theta r cos of alpha minus theta r. Cos of alpha minus pi by 2 minus theta r can be written as cos of pi by 2 plus theta r minus alpha, and cos of pi by 2 plus theta r minus alpha is nothing but minus sin of theta r minus alpha, which is the same as sin of alpha minus theta r, and therefore Fd plus Fq can be written as f hat multiplied by cos theta r sin alpha minus theta r plus sin theta r cos alpha minus theta r. So, this is of the form sin A cos B plus cos A sin B, and therefore, this is f hat into sin of alpha minus theta r plus theta r, which is nothing but f hat sin alpha, which is the waveform that we have drawn here, and therefore Fd plus Fq gives you the original MMF back. To represent the whole thing in this graph, essentially what we have done is that maybe take a green. Now, we see that the rotor has moved to some particular angle theta r, and therefore, the pole face axis would lie somewhere here at this angle, and f hat into cos of theta r would then give you this magnitude, and therefore, what we are assuming is that this MMF on the direct axis is distributed as a sinusoidal function like this in some manner, and then another term f hat into sine of this angle would come somewhere here, and then you have another sinusoid which is something like this, and then we are saying that the sum of these two sinusoids is the original sinusoid. So, that is a pictorial representation then of this expression. So, if we then look back, what we have said is that the salient pole rotor can now be thought of, the machine with the salient pole rotor can now be thought of as having a machine with two cylindrical rotors, one cylindrical rotor being associated with a small air gap and being representative of the interpolar regions, and one cylindrical rotor being associated with a large air gap being small air gap being representative of the pole face regions, and another rotor being associated with a large air gap representative of interpolar regions, and we need to add the two fluxes that are going to be generated. Now, having come this far, let us now see what we would do to arrive at the fluxes that are generated. Now, let us say that the air gap along the direct axis air gap representative of the direct axis is LGD. LG was the air gap that we had used here. We use the suffix D to represent direct axis, and then the air gap representative of the quadrature axis, let us call it as LGQ. So, if this is the case, now we are considering two cylindrical rotors having a uniform air gap of LGD and LGQ. Along LGD the MMF FD is acting, along LGQ the MMF FQ is acting. So, in order to find out the flux that is generated, we need to divide the MMF by the reluctance. And how do we find out the reluctance of the air gap LGD? That is nothing but, let us call it as RGD, is nothing but LGD divided by mu naught into area. Now, how do we get the area? We will take the approach that we have used earlier. If you remember, in order to find out the flux passing through a particular area, let us go back to our figure of the last lecture. Here we have it. In order to find out the flux that is passing through a particular area, what we have done is we considered an elemental small area that lies along the axial length of the machine, and the arc here is subtended by a small angle d alpha, which is at a particular angle alpha from your reference alpha axis. So, we use the same approach here also. Now, let us say we want to consider the flux, at a particular angle alpha, then we consider an elemental angle d alpha, and along the axial length of the machine, the area associated with that will then be r d alpha, that is the segment length, multiplied by L, that is the axial length of the machine. So, this gives you the area of that small elemental segment. LGD by mu naught into that area gives you the reluctance offered by a small portion of air gap having this area. Similarly, you would have RGQ, which is then given by LGQ divided by mu naught into R L d alpha. Note that if you see the difference between RGD and RGQ, it arises due to the air gap only, otherwise the rotors are of the same dimension, the two equivalent cylindrical rotors, only the air gap is different. So, this then helps us to write down the flux that is generated. the flux generated at this elemental area due to the d axis is then given by Fd. Fd is a function of alpha, that means the direct axis MMF distribution is again sinusoidally varying around the air gap. At a particular angle alpha it would have a certain value, and that value divided by the reluctance RGD gives you the flux that is generated due to the direct axis MMF. Add that to the flux that is generated by the quadrature axis MMF. To get that you have to divide by RGQ. This is the flux that is generated at this angle alpha passing through this elemental area. Now if you want to find out the flux linkage due to this flux, then d psi s is nothing but the number of turns in the stator multiplied by this d phi, it is d phi d plus d phi q is what we have written. So this is just d phi ns multiplied by d phi, and therefore this is ns multiplied by Fd alpha by Rgd plus Fq alpha by Rgq. Now this is the flux linkage caused due to the elemental flux that is crossing that particular area. Now the MMF is distributed all along the circumference. Again let us go back to the figure of our earlier lecture. In order to find out the flux linkage of the stator coil, we need to integrate over the area spanned by the stator coil. We did that in the earlier case also to find out the flux linkage, but there the flux was generated by the rotor and the flux density waveforms are constant and so on and so forth. But now we have determined how this MMF variation is there, and due to that MMF with the two cylindrical rotors we now know what is the flux that is going to pass through a given elemental area, and in order to find out the total flux passing through this area and therefore linking this coil here, this coil, we have to integrate from alpha equal to 0 to alpha equal to pi, and therefore that is exactly what we need to do next. In order to find out the total flux linkage psi s, that is nothing but integral from 0 to pi of d psi s, which is ns multiplied by integral 0 to pi Fd of alpha we can get from our earlier expression. So Fd of alpha is f hat cos theta r multiplied by this. We have reduced that to sine of alpha minus theta r. So this is f hat cos theta r multiplied by sine alpha minus theta r divided by Lgd plus f hat sin theta r multiplied by cos of alpha minus theta r divided by Lgq into mu naught r L d alpha. So this expression we have to integrate in order to get the total flux linkage, and then flux linkage divided by the excitation current Is would then give you the inductance. So let us do this integration in the next class and see what is going to be the nature of the inductance and whether it has any approximation to the inductance variation that we have already seen. We will stop here for today.